Hey there.
Hello.
Hey, have you been waiting in the room for like 10 minutes since 7?
Yeah.
Okay, yeah. I had the meeting from yesterday. It didn't update in my thing, so I don't know why that
Oh,
is.
okay.
I'll have to fix that, but we can definitely make up this 12 minutes or whatever at the end if you're available. Um,
Yeah.
if not, we can work it out. But once you get your, full time, of course. Yeah. Anyways, um, yeah. How's it going? Did you were you able to? I saw you sent some stuff from your notes, basically. Were you able to get any more information on the exam?
So the exam is going to be changed to Wednesday. I don't know
Oh,
why, but he just changed it. So, I mean, that's good that I have extra
yeah.
study time.
Hmm.
But he did say that it would be a few math questions at the end, and then majority of it is like what we have in our notes. So
Okay.
I kind of sent that to get like an idea.
Yeah. So that makes sense. So it's qualitative, as in like this is Newton's second law, or describe
Yeah.
something, describe
Hmm.
Kepler's second law, or whatever. That's good because that math is hard sometimes if you don't practice a bunch of it. So
Yeah.
yeah. Did you want to just kind of go through the notes, or what were you thinking?
Yeah, if we could do that, that would be great.
Sure. I can just start at the top here. Are you? I can share and are you like more of a visual learner or an audio person or both?
I think visual.
Yeah. Okay. So that's good to know. I'll definitely write a little bit more because I don't know if you realize that I like to talk about it. Okay. So on the first page, I don't know if you got it in front of you, but to me, the most important thing here is the third. I'm looking at the notes that you sent in the thing. The most
Hmm.
important thing is Newton's second law, right? And that equation right below it is Newton's second law, where usually it's written like this. Are you able to? Do you
Yes.
see my screen?
Yeah.
Okay, cool. And that makes sense, right? And the acceleration of a body is directly proportional to the net force, but that's I don't know. It's not that as important as saying add up all the forces and that's your acceleration, right? And so that's what you'll
Hmm.
have, because you might have a force. Do you guys do in vectors? How much are you into vectors, and how familiar is that word?
Um, we haven't really done that at all.
Okay, okay. So that's good for you because it makes it more complicated. But so F net, but what does that mean to you? Like the net part. Do you know what that means?
I've heard of it.
Yeah, so it means total. And it has to be
Hmm.
kind of in the same direction. So if you have one force and let's say it's 10 newtons, right? And that's
Hmm.
great. And if that's your only force and you're given some mass, right? Well, kind of like we were
Hmm.
saying before, we extract the information and say it's just 10 kilograms. Well, we know what the acceleration is here, right?
Hmm.
Because F net, this is the key point here. F net is the sum of all forces. And if you only have one force, it's just equal to F1 or 10 newtons.
Hmm.
But of course, this is M, A, and I'll do the algebra for you. So if I wanted to solve for this, right, then you divide both sides by M. And then A, for this just random case, right, well, 10 newtons divided by 10 kilograms is just 1. Do you know the units for acceleration?
Um, Seconds?
So seconds is time, always time, but seconds
Oh.
are involved in the acceleration, definitely. I'll give you they're down here in the denominator, and they're squared. And then we have
Oh, meters
meters.
per second?
Yeah, meters per second squared.
Okay.
And meters per second is a velocity. And think of like your car odometer, miles per hour, but miles divided by
Hmm.
hours. But more importantly, that it's a length divided by a time, right? And
Hmm.
so I don't care what your units are. Meters per second is a length meter divided by time, right? So we won't get too much on that, but that's fair. That's helpful to think about that. Okay, so let me not erase that. But let's say we have another force, right? And let's say it's going this way. And now we call this guy F2. And now this is where it's kind of a little more interesting, where we say F net. And let's say this one is 5 newtons. But notice that it's going in the different direction. And so pretend that this force is acting on an object, right? Let me make it a little more clear here. So my force, we have one force going to the right, 10 newtons, right, for us. And then this other one is going to the left. F2 is 5 newtons. That's how this plays out, right? These things act on the point, act on an object. And so what's the acceleration? Well, it's not just 10 divided by the mass down here, right? Because F net is no longer equal to F1. F net means F1 plus F2, or as many forces as you have. So that's what I'm trying to drive home here. I don't care how many there are. It could be 1,000. You're not going to have that, but just the idea behind it, right? It's as many as there are. And another thing here is that we would do 10 minus 5. That's actually equal to the F net. I know I'm getting a little busy here, but is that part kind of clear for this problem here?
Yeah.
Okay, good, because it's going in the opposite direction, right?
Yeah.
Okay. So yeah, that was what I saw here on Newton's second law. Are you pretty comfortable with Newton's second law? Do you want to move on, or?
If we could do just a little bit more.
Yeah, sure, of course. So which part do you find most helpful? Just kind of talking about it in general, or the math part? I guess the math part might be the most helpful.
Yeah.
Okay, yeah. So yeah, that they might give you a problem actually on the end there. And if you're not dealing with vectors and gravitational force, right? This happens here. So if you have some object, say it's just falling, and so, well, there's gravity acting on it when it's on the Earth, or I don't care where it is, Mars or the moon. And yeah, we call this, you guys call this FG. I think it's big F for you guys. But again, so what is F net for this situation? I haven't drawn much, but there's an F net here. And what is F net? If you were to write an equation and say F net, what is this equal to? I'm asking.
Wait, I'm confused. What?
So all I want to know is, what is F net in this case here, just this case right here? What would F net be equal to? So remember that F net is the sum of all forces acting on an object, right? So if this is the point is usually represented, sorry, I should have been more clear. This is the point, and I have this force acting on it, the gravitational force acting downward. So what is F net if it's the sum of all forces on an object?
Would it be negative?
Yeah, it would. If you gotta be careful. Yeah, that's the right idea. If you say that the positive y direction is up, then yes, it would be negative. So we can write a minus sign there. But what do I write here? What is the kind of thing that I write? Just FG.
Oh, okay.
Because it's the sum of all forces acting on the object. Right now, I only have gravity. And so I guess my mind went to connecting this equation, which hopefully you recognize as Newton's second law, right? But then there's also an equation, I'll use a different color here. This equation, which you're familiar with, or you have to know, I guess, on your thing. Do a little better. Universal law of gravitation, right? And so there may be something that relates these two, because I know that they look different. What I mean is the gravitational force and the net force acting on an object, which is the sum of all forces acting on that object. But I've just shown you an example that you might very well see that, well, this is the total force acting on this object. It just happens to be gravity in this case, right? So hopefully there's a connection between these forces can be one and the same. And there can be, F net could be, if I decided, say I got a crane, whatever, I started pulling up on this object, right, with some force, F1. Well, now F net is going to be F1 positive like you said before, because FG is negative, that's downward. And then the upward direction has to be positive then. So that means it's plus F1 minus FG. And the only
Okay.
reason is because F net is the sum of all forces, meaning add up all the forces.
Okay.
So you might see a lot of that where forces are acting in the same direction or the opposite direction. And as long as they're acting in the same direction, either positive or negative Y, you can add them up, like this situation here. Sorry, I should keep everything. But the same thing might happen. Let me draw a different situation just really quick here. There's my object. We treat it as a point mass, usually, where all the mass is distributed at this point. And so I say, okay, well, I'm going to pull on it. I'm going to do something to give it a force. Which direction? Well, in this direction. I'm going to call that positive X, that way. So F1 is in the positive X direction. Great. And then F2 is over here. So that's minus X direction. You may not have to worry about that if you're not dealing with vectors. I don't know if you guys talked about that, the X and Y direction, a lot when you were doing your problems. But just the simplest fact here is that F net, it has to be the sum of everything. It's not F1, it's not F2, right? It's F1 minus F2. And if it's not clear why, please tell me and clear it up really quick, hopefully.
So if it's the sum of everything, then why is like it F1 minus F2?
So that was because we called this the positive X direction. And so to the right, to the right here would be a positive force. And it doesn't matter. I don't want to confuse here, but I could have said this. What I'm saying is that I just chose to the right was the positive X direction. But if I said this, then it would be backwards. It would be F2 minus F1. And the thing is that you get to choose based on the problem. And let me show it one more time. Just this is what we had originally. I said that was the positive X direction to the right. And so that means, well, if I add the forces, it's positive F1, and then it has to be minus F2. Why? Because it's going in the minus X direction. And so I would be surprised if that didn't show up on the test, honestly, like that, because F net is the sum, so you have to add. So you need more than one force, right?
Yeah.
Is it becoming a little more clear, hopefully, about Newton's second law and how to use it? Okay.
Yeah.
Do you want to go over anything else for Newton's second law? It's an important one, but I don't know how much you guys are doing on it. If you're not dealing with vectors, you honestly probably have everything.
Yeah, I think I understand everything.
Okay. Yeah, if we meet again, I'll definitely go over it again, just a little refresher review, to make sure. Does he happen to give what the percentage is? Like Newton's law will be 10% of the test and Kepler's laws will be 20%. That would be nice. I don't imagine.
Yeah, he doesn't really give super clear ideas of what the test would be.
Have you taken a test with this class with him before?
Yeah.
This semester or this whatever year? Was it, how was it? Was it like what you covered in class? Did you find it kind of easy or?
Yeah, I think it was mostly what was in my notes, which is why I sent that. So we could just look over it.
Yeah, sure.
And then towards the end, it's like math problems.
Right. And okay, good. So yeah, because there's quite a bit here. I'd like to work on whatever you are weakest in. Because if it was up to me, I just go down to whatever I think is the next most important thing, but that may not be like what you think you need to work on.
I think I should review all of it so we can do what's ever next.
Okay, yeah, I'll try to manage the time here because Newton's law is important. Okay, directly proportional. That's a good phrase. Do you understand that one? That's from math. That phrase, directly proportional. Are you okay on that?
Yeah.
Yeah, okay, good. And think about Newton's second law, right? If F net goes up, well, that means acceleration goes up, right? Because they're directly proportional. And then, yeah, inversely proportional, just the opposite. So if one goes up, one goes down. That's pretty easy. Net force we covered pretty good. It does say vector sum of all the forces. Cosine sine, does that ring a bell? I mean, I don't. What are you, a junior, or what grade are you in?
Yeah, I'm a junior.
Junior. So have you taken trig? Or are you going to take that? Like, are you taking it now? I guess is what I'm asking.
I did that last year.
Okay. It wasn't geometry? You
Well,
did
it was like
trigonometry.
both. It was like a
Oh,
hybrid
okay.
type thing.
Oh, interesting. Yeah, because the vector sum, that's when you get into it's definitely more complicated, but it doesn't sound like you're doing that. So,
Yeah, I don't think so.
okay. Does this mean when an object has a force exerted, it accelerates? So do you understand that sentence there? Like why that answer is no? I'm looking at just under net force. Does this mean when an object has a force exerted on it?
Let me see.
Because it's important why the answer is no. Did you find it's like in the middle
Yeah,
of the page.
oh yeah, okay, I found it.
Okay, yeah. Do you understand why the answer is no?
Kind of. It's still a little confusing to me.
Okay, it's okay. We should talk about it because it has to do with F net. This is literally the reason. F net. We can write this MA if you want, but you don't really need that part. F net. Imagine I have my object. This is the standard thing that you're going to think about and see, or you should think about when you're thinking about forces in Newton's second law. I got a force. Let's give it a number so we can better understand it. 10 newtons. There's a force being exerted on this object, that object, and this is the force. Make sense? But what if I say this? Now there's two forces. That's why I say F2. And then, well, let's give it a minus sign because it's acting in the opposite direction as F1. Hopefully that's clear. Now, what is F net?
Would it be negative 10 newtons?
It'd be 0.
Oh wait. Yeah, okay.
Is that, are you good with that?
Yeah.
Are you sure?
Yeah.
Okay, good. Because that's exactly right. And we do F2, F1 minus F2, just because F2 is in the minus direction. And so you do 10 minus 10. Same forces acting in opposite directions. There's nothing happening. And that's what that means. That's why the answer to this question is no. Because think about it. Does this mean when an object has a force exerted on it? Okay, exerted, whatever. But I have an object, great. And here's a force. So that little sentence is satisfied. There's a force being exerted on this object. Does it always accelerate? Well, no. And I just showed you why. Because of, I don't care about any single force. That's the main point to all this. It's the sum of all the forces acting on the object.
Okay.
And then that sentence below it, during a tug of war, both teams exert power, the rope will not change if they exert the same force. I mean, this is the same exact thing here. Let's I know the numbers are helpful, but here's my team. I got whatever, five bros on this side, and then 5 bros on this side. And they're exerting the same force on whatever the middle of this rope is, but it's not moving. If nobody's moving, then net zero force. That's where all these things. Net force.
Okay.
Net zero force, zero net force means all of the forces acting on a body add up to 0. And so, yeah, all these things are just kind of a different way to think about the same thing. If I could, I would draw a bracket starting at the 3rd bullet point where it says Newton's second law, and then draw it all the way down, basically, down to just before force versus pressure. No net force means no acceleration. Like Newton's second law, and all the way down there is like one idea basically that is describing Newton's second law. Yeah. And just on the last thing on that is just, it's the sum of all forces, and it always is, and it's never anything else. So even if there's there's only one, then it's your force, right? But that remains always all the forces. Okay, and then we get into pressure here. That's just an equation. Hopefully, that's okay. When we get in here, we say, does it help you to write when you're learning about this stuff? Does it help you to write the? This is a little tip. Maybe it'll help to do this. Pressure equals, force divided by area. Because this, if you're not used to it, it's like P equals F over A. What the heck is that? I don't understand. What's F? I don't know. Until you actually remember. Oh, right, it's force. That's just a little tip when you're first doing it. It doesn't sound like, okay, here you go into the units. More force makes more pressure. This is literally, if you go back up and you're talking about direct proportionality, that's what it is. I'm looking at the bullet point right under your units, lbs per inches squared. More force makes more pressure. That's literally direct proportionality. And the way you see this, we're talking about the direct proportionality, is that this is in the numerator and this is also in the numerator on the equal sign. That's why. Hopefully that helps a little. Because I mean, I could say this is, you can divide anything by 1, right? I didn't change anything. And so this is in the numerator again, and this is in the numerator. Standing up, less area for weight to be distributed over versus sitting down. Okay, that makes sense. Yeah, so yeah, the more area there is, the less pressure there is. And that's literally, let me write this. If this goes up, if area goes up, this thing is going to go down simply because of this equation here. And this green here is called indirect, or I think you said inverse. Let me scroll up. Inversely proportional. And direct, this is good here. Direct, same color, and then inversely proportional. That's inversely proportional. This is directly proportional. And I should continue here, because I shouldn't just stop there, because it's like, well, yeah, that's cool. So what that means is exactly what they're saying. If there's higher pressure on the tire, well, if it's a smaller tire, there's less area to push on, meaning that there will be higher pressure, right? Or say that you have, how do I think about this? If you have, this is the pressure on a tire, 10 PSI. You guys do that? Yeah, PSI, pounds per square inch, great. And so if I want to figure out the force, but I'm given the same pressure. So let's say I have a small tire. So it's not too weird for you to use these, to not use numbers down there. But then let's say I have 10 PSI, but what's the force now on a large tire? That's really what this last sentence is talking about. Given the same pressure, how does the force respond? Well, if I have a smaller tire, that means that this guy has to be bigger. This F has to be larger than this F here. And the only reason is because there's more area for it to push on. Where I have, here's a big tire, small tire. We can think about the pressure pushing. It's literally pushing kind of from the center at all points on this tire, right? But now do the same pressure. Remember, we're going to use 10 PSI in white, 10 PSI. But I have to have a larger force on this guy here. Because the tire is smaller, has to have more force on the surface of the tire, the edges of the tire. You can think about it.
Okay.
Okay, now I'm looking at Newton's third law here. Yeah, these are good. Yeah, these examples are good to think about. Are you, I don't know if you have ever fired a gun or hunted or whatever, but that's a great example of Newton's third law, right? I mean, this bullet is going out incredibly fast. I mean, it's so fast. That's why it's so dangerous, right? But like, it goes out so fast, but something has to happen. And that's Newton's third law, because if the bullet goes one way, oh, this is a good, let me draw this. So yeah, I'm a math and physics person, not an artist. So you have your bullet, right? Let me do that better. The bullet is here and it's going this way. But Newton's third law says for every single force, there's an equal and opposite reaction. And so Newton's first law, right? So Newton's first law tells us that this thing's not going to move unless a force acts on it, right? That's the basics of Newton's law. Something's not going to happen unless a force acts on it, or the net force is non-zero. There's not going to be an acceleration. So that's what Newton's first law tells us. But then Newton's third law comes in and says, well, for every force, there's an equal and opposite one. So what does that mean? Well, there has to be one equal and opposite in the other direction. That's what opposite means. Same magnitude, or if it's 10 newtons, then it's going to be also 10 newtons in the opposite direction. That's why you feel the recoil. Like I said, I don't know if you've fired a gun, but like there's recoil on your shoulder or whatever you do. And if you don't know what you're doing, then you can get knocked out, right? There's plenty of videos on YouTube and TikTok, right, where people don't know how to hold a gun and then it hits them in the stomach. And that's literally because of Newton's third law, right? Similar velocities. Yeah, that's what they talk about. That's good. Is that concept pretty clear about the different velocities? Seems like they talk about that a lot. And it has to do with mass, right?
Yeah.
The same force, if we look at F net, let me see. Newton's second law, this is probably the most important one. But if I have some force, F net, we're going to say equals 100 newtons. So direct proportionality, that phrase, it tells us, well, what if I do 100 newtons on an apple, which weighs whatever, 1 kilogram, I think. Okay, great. You can put it in the equation and to figure out the acceleration. I can do that real quick. It's 100 F net, because if I divide both sides by m over here, then A is equal to F net divided by m, right? So I know I'm going quick on the math here, but please slow me down or stop me if it's not clear. But my acceleration here then on the apple is 100 newtons. I'm sorry, 100 meters per second squared. Okay, great, fine. But say I have 100 newtons on something else, like a book or a cat, a large cat, or a house or something. And so we're talking about the same thing, 100 newtons, but now on, a house isn't a great example. How about a car? I don't know. This thing weighs a lot, right? It's like 20,000 kilograms, I guess. Who cares? Who knows? Use the same exact equation and you get, well, 100 divided by 20,000, or what is it, 2 times 10 to the 4th? Well, the acceleration is a lot smaller. And since velocity and acceleration are related, it's going to have a smaller velocity as well. That's what this idea is here with the gun and the bullet, right? Okay, let's talk about football. Same type of idea, right? It's probably imagine a giant football player, knocking out some tiny guy. Same force, exact same force, but that big guy's not going anywhere because of his mass. It's a larger mass. Car hits mosquito, same thing, right? weight, SI units. That's good. Changing location. Yeah, that's a mass never changes, at least for you. I mean, yeah, go get a PhD in particle physics if you want to deal with that. So mass never changes. I think hopefully you're probably okay with that, right?
Mm-hmm.
And that's related to that idea with the universal gravitation that we were doing. Like this astronaut is 84 kilograms in space, but he's also 84 kilograms on the Earth. And it's the gravitational force that changes.
Mm-hmm.
Force and acceleration change. But never mass. You're whatever you are, 50 kilograms, or an apple is always 1 kilogram. I don't care where it is in the universe. Friction time. Oh, but this is what you're talking about. Okay, this is good here. The force that opposes the relative motion. Okay, that's good. Just this is kind of a qualitative thing, since we're doing much of the math. If I have a box or anything really, and I have a surface, right, and it's moving with some velocity to the right,
Mm-hmm.
which direction is the friction? If I was to draw an arrow, which direction would it be in?
The opposite.
Yeah. So usually we draw this like right here or whatever, kind of on the
Mm-hmm.
bottom to note that it's between the box and the floor, but it's probably okay to do it in the middle, But yeah, okay, good. You got that. It always opposes velocity. And this is, so you see this one, right? This is horizontal, but what if I have, some ball, I guess, and it's under the force of gravity? There's your FG, right?
Mm-hmm.
Gravitational acceleration, little g. Which direction is the friction force now, if there's air resistance?
The opposite direction.
Opposite direction. So left, right, up, down.
Oh, up.
Yeah, you got it. So and like these look different, but they're not. I got just rotate your page, right? And it's the same
Mm-hmm.
when you're dealing with friction. Friction hates motion, right? So this is a good, the faster something moves, the more friction there is in general, to a certain extent. Yeah, for this, definitely. The faster you're moving, or the larger the acceleration, the larger the friction force is. That's a good little side note. Means that's what that means by saying it. Friction hates motion, wants everything to be at rest. Yeah, doesn't get things moving, makes sense. Okay, static friction. How's that idea between static and kinetic friction?
I have a general understanding of it.
Yeah, do you want to spend a minute or two on it, or move on?
Yes, please.
Okay, sure. So kinetic is when it's moving, and that's actually what both of these guys are right here. This is kinetic friction. I'm just going to use the color that I was using for friction, right? That up arrow and the left arrow was friction. I'm not sure what you use, but I use FR usually. So that's kinetic.
Mm-hmm.
And all that means is that the thing's moving. That's kind of like kinesthetics, like you're a kinesthetic learner or an auditory learner from high school or elementary school. And so kinetic means motion, right? And so if something's moving, there's no static friction. You forget about it. It's kinetic when it's moving. And if it's at rest, then it's static. So it's kind of like a binary thing. If it's just sitting there, the static friction is exactly what it says. It's the force that keeps it at rest. You have to overcome this friction. Say I have a box sitting here, but now it's not moving, right? Now velocity equals 0. So, but if I want to get it moving, well, I'll exert a tiny little force this way. Oh, darn, it wasn't enough to get it moving. And the reason is because I did not put enough force on it to overcome this friction force.
Yeah, okay.
If I want to get this guy moving, I have to make it bigger. That's so a longer arrow for a larger force usually, but I need to overcome that friction force for the static. This is what that's what static is. This one, static friction. Subtypes, yeah, this is, I doubt he's going to have anything on this. Sliding friction, fluid friction. I guess one thing to say is that the fluid friction would also be air resistance. It's important to think to know that air is a fluid, right? for physics and chemistry someday, that air, a gas in a liquid is defined as a fluid, really. So air is a substance that conforms a container, can flow. Great. Did you guys talk about pressure in fluids? Because that is a thing.
A little bit.
Okay. Liquids, gases, and plasmas are fluids. So yeah, there you go. Great. Doesn't see it there, but it really is the same equation. If you go back and you say, if you have some fluid, there's my water, right? Let's call it. And so the pressure, which is P equals force divided by area. F is force, A is area. And so you just take a little piece of this guy here. I won't get into this too much, but it would be, you could do the whole area of this whole thing, right? That would be the area, the surface area of the thing. Or you could take a little piece here. But what you're going to get, you're going to find is that it's uniform and that the pressure is the same no matter how big of an area you take. And this could be a container of air, a container of carbon dioxide. It doesn't matter, right? As it says, liquids, gases, plasmas are fluids. That you'll be dealing with any plasmas. That'd be cool. Fluid is a description of behavior boat. Yeah, that's good. Anything, honestly, any movement that you encounter or can think about, unless you're literally not in an atmosphere, right? But if you slide a box along the thing, there's, yeah, of course, kinetic friction. And I guess it would be one of these things, sliding friction, there you go. But also a boat. I mean, there's motion and there's something that wants to slow down the movement. That's what we call friction. Boat, box, anything going across. Kind of the thing that they like to use is a frictionless surface is like an ice rink. If a skater is going across ice and you see how smooth they are, I mean, besides how good they are at it, right? But they hardly slow down at all.
Yeah.
Because there is some friction, there's always some friction, but there's just so little compared to, slide your hand across the table right now. And it's like, and if the harder you push, the harder it is to move, which goes back to that idea of the more force you provide, the harder it is, the harder the friction force works, right? You can do that like right now and just push your hand lightly, and it's pretty easy, obviously. I mean, this is, 5-year-old knows this, right? But then push your hand all the way down almost, and it's harder and more friction.
Yeah.
Friction behaviors help explain it's hard to get something to keep it. Yeah, related to Newton's first law. Okay. Hopefully these notes are useful here. And then talking about gravity and distance. Oh yeah, this is the most recent stuff too. So, okay. Yeah, I like to think here because what did we talk about? We talked about pressure equals force over area, gravity, the gravitational force. There's your constant, some masses, distance squared, and then you can have that other one, mass of the earth, r over h, pretty much the same equation. These things are all forces, and they're all related to Newton's second law. And gravity is the same thing, and you can use that gravitational force. That's what I was trying to connect for you in this guy here, this example that I made here, is that F net is related to the force of gravity, as well as it could be related to the pressure force too. We'd have to have a problem to see how that works, but just think about that qualitatively, that it doesn't matter, that they're all forces, even though the equations are different. You're even using a different letter, big F and lowercase f. I don't care. It's still a force. And literally everything we've talked about for the past hour applies to this whole section on gravity, Gravity all. What is that? The war page is what creates the pull. What is that word on? It's not that important.
For gravity and distance.
Yeah, 11/2 gravity. It's like 1, 2, 3, 4, 5, 6, 7. The seventh one. 7th bullet point. I'm just wondering what that word is.
Oh, masses existing in space-time causes warpage and
Oh,
distortion of the
warpage.
fabric.
I see. Yeah, yeah. Oh, that's Einstein's theory, right? That's a great video. I don't know
Yeah.
if like think about a net, a video. Just say all these words, but like a net, picture a net really taut over some surface. Then you drop a ball. Well, of course, the ball is going to sink in the net, right?
Yeah.
And according to Einstein and all those really advanced theories, that's literally what the Earth does to the space-time fabric, and that's what they're talking about here. Force field, space-time, like, and so that's good, so if you have space-time, that's what this little net is, and then the Earth, put it right in the middle. You need 3 dimensions, and then, like I said, this thing will sink down, right? And then imagine putting another ball in here. Well, it's gonna go like this. It's gonna spiral around, right? And that's what the moon is literally doing, as well as the Earth around the sun, where the sun is this giant mass that distorts the space-time fabric. It's pretty crazy, and honestly, all the math supports it. Apparently, I don't. People smarter than me can actually do it, but it's pretty wild.
Yeah.
Gravity and did you want to talk about any more of that? Gravity and I want to make sure we cover everything here because we still have a few minutes, or about 10 minutes. Did you want to talk about gravity anymore? 11/2.
I don't think so. I think I'm good on that.
Okay. The equation, yeah, the math. Hopefully we can get some more problems if you want to meet again before this. Gravity and distance. Okay, yeah, this is a good one. The astronauts, we spent some time on the math here, but hopefully the concept is there. And yeah, weightlessness makes sense. It's really weightless. It's interesting. Maybe this is helpful, but imagine it's actually related to this equation here. So we're sitting here, or whatever you're doing, you're laying down, you're sitting right now, you're sitting on the surface of the Earth, right? And so this thing literally applies. This equation, you can calculate it and figure out the force being acted upon you. It's your mass times gravitational acceleration, just happen to be the same. But then say you do go up into whatever it's called, well, you could do the SpaceX thing, whatever Bezos is thing in, what the hell is that called? Blue, I don't know, whatever he's going to space. And it's not that, my point is, it's not that much farther. Like, here's the center of the Earth, right? And you're sitting here. This is where you are literally right now on the surface of the Earth. You're on it, and this is the distance from the center. That's why you use that RE when you're calculating this thing here. I forget, whatever that is, kilometers, the radius of the Earth, right?
Yeah, I think so.
That's what this thing is. And you can plug that into here as the distance for your gravitational force. But then this guy says, well, I'm going to go up into space. I'm going to go up into where I'm experiencing weightlessness or microgravity. And so it's right here. Maybe it's not even really that far if we're drawing things to scale. So that distance there is h. If the h in that equation, right, we have to add that distance in our equation. And so I think we went up 500 kilometers the other day or yesterday. And then, say you go up 250 kilometers, h. That's a very small amount compared to this thing. How could that make a difference? Why don't we feel the gravity, right? It's actually because the atmosphere is pushing down on you. It's not because there's really any less gravity. It's a tiny bit less, right? But we're sitting here because of the atmosphere. We'll always feel the gravity, but we don't float off because there's actually a lot of weight sitting on you right now because of all the molecules and crap floating around in the atmosphere. It's heavy. So it's pretty interesting. And hopefully it helps you think about these equations too, that they really are the same. And what that H kind of means, when you get some height away or some distance away from the surface.
Yeah.
We talk about satellites. That's cool. Fall for years, not in the ground. Yeah. Should we talk about this? The curve. the intended path, that inertial path, that's important there, because this is literally Newton's second law at work here. Let me see if I can draw this real quick. Earth. And then actual path, and then that's what this little dashed line you've written here, like the inertial path. And it always goes back to Newton's first law. The inertial means, well, what if Newton's first law was true? No forces are acting. Well, yeah, if no forces are acting, it doesn't change direction. It just keeps going where it's going. That's why that's the inertial path. It's literally Newton's first law in action. But we say, no, the Earth is, this has a gravitational force, Fg, due to the Earth. That's why it has this curved path here. So it's all related. And it becomes a curved thing. That's the satellite. And yeah, if the velocity is fast enough, I mean, I don't know if you've heard, but those things are moving whatever, 10,000 miles an hour, some ridiculous amount. And they have to, right, to get up there, number one, but also so they don't fall back down after time. This is good stuff, because it really is all related back to Newton's laws. This is like an application of just Newton's laws dealing with satellites and Earth. So hopefully that helps a bit. Now I'm looking at Kepler's laws. Let me go past that real quick. Okay, yeah, Newton's first and second law, great. Oh yeah, okay. So Kepler's laws, if you still have 5 minutes to make up for the beginning here, we can talk about Kepler's laws.
If we can, that would be great.
Yeah, okay. So Kepler's first. Sorry, my writing gets worse as we go, apparently. Kepler. Okay, all right, yeah. So an ellipse, you know what that is? Do you know what ellipse is, pretty much?
Yeah.
Yeah, just an elongated circle, whatever. Or one, if you have the center here, we call this the semi-major axis along the fat end, and then the short end is the semi-minor axis. So semi-major. And I promise there's a point. Normally, it's like, cool, I don't care what they're called, but the foci, that's what it says. This is Kepler's first law, right? The orbits of the planets around the sun are ellipses with the sun at one focus. Foci, if there's two of them. So the focus, like this is the center of our ellipse, and this path, of course, would be the Earth, let's say. And so how you think about it, the center is not the foci, the focus. The focus is these 2 points, and it's like it's where the distance between the ellipse and the center is the same. That's not right. It sounds something like that, where the focus is. Let's see if it's on here. Yeah, the point of the focus, and there's 2 of them always, but the focus of the ellipse is always the point. Something wrong. Ellipse, 2 fixed points on its major axis, the sum of the distance of any point. Okay, all right. It's the sum of these distances at any point on the ellipse. I don't even know if I should. This is something you can look up, and it might be helpful, because this is where the sun is, right? That's the point of Kepler's first law. Sun is here, and all the focus means is that if I have one here and right here, these points, if I pick any point on the ellipse, say that point, I'll pick that point. Well, the sum of that distance, this one and that one, is a constant. And so if I pick that distance, well, the sum of, if I pick that point on the ellipse, the sum of that distance and that distance is a constant, happens to be the same constant as that one. So I know that's a little distorted, but and then the sun is there, and you can have the Earth. And the point is here too is that the moon orbits the Earth in basically the same way. But the most important one that I should start with since is Kepler 2. That's the one you really want to know if you are strapped for time or whatever. The second one is the one you want. Equal areas in equal times. Those are the words you want. And what that means is that if it's in its orbit here, and let's make it even a little more interesting. Well, the application of this equal area, right? If I have this thing here, because these are two positions on the ellipse, and if two positions happen, I have to have some amount of time, right? Delta t, that's where
Hmm.
the time comes in. And so what is the area? Well, if you take these points of this, it's not really a triangle, but this whole shaded region, right? Large area, and so it's some a. Well, equal areas and equal times. Say I want to go over here. Say I choose that one, right? But this delta t is the same, so it actually needs to be bigger there. And I say, okay, this is the same delta t. What I mean is that the same time has passed, time 1, time 2 over here on the ellipse, but the same time has passed between those positions. Okay, if that's true, then this is the same area of the ellipse. That's all that means.
Hmm.
And so the most important consequence of this is that, let me redraw it here. What that really means is that if you have your thing, is that the object or the planet moves slower out here. This is its orbit. And as it gets closer, it's got to go faster until it's really fast around there. That's what that
Hmm.
means. So equal areas, equal time, kind of confusing, but it is helpful. But this is the consequence. When it's right here, it moves much faster than when it's way away, especially if the ellipse looks like this, right?
Hmm.
Okay, so hopefully we did happen to cover everything pretty much on this. And we made up for our time too, so sorry about that. I'll if we meet again, I'll definitely pay attention so you're not waiting around sitting for me. So
Oh, it's okay. Don't worry.
yeah, okay. If you're able to tomorrow, try to get some problems, or Friday, I guess, too. See if he'll give you some insight or some more practice problems, maybe. Um,
Okay.
so you can get the math. All right, thanks. Appreciate it.
Okay. Thank
All
you.
right, see you. Bye.
Bye.